Imagine a machine so small you could hold it in your hands, yet capable of generating more power than some full-sized engines you see on the road today. Welcome to Maxwell Chikumbutso's workshop, where engineering defies conventional logic, where the mantra isn't bigger is better, it's smarter is stronger. Today, we're diving deep into the tiny engine Maxwell built and why its output is simply unbelievable. At first glance, it looks unassuming. A compact metal cylinder, a few wires, a couple of pistons, precision-milled components, almost toy-like. But appearances are deceiving. This is not a standard microengine. It's a masterclass in energy efficiency, torque optimization, and materials engineering. Maxwell started with a simple challenge. Can we create a power unit smaller than a motorcycle engine that still produces industrial-grade output? Most engineers would have stopped at theoretical calculations. Maxwell? He built a prototype. The design philosophy was radical. Compact frame. Every millimeter was optimized for airflow, heat dissipation, and vibration control. Advanced metallurgy. Microalloys that can withstand extreme pressures without adding weight. Energy recapture. Braking and compression cycles harnessed to feed back into the system. And then came the true innovation, the geometry of the combustion chamber and the precision timing. Maxwell didn't just tweak existing designs. He reimagined the internal dynamics entirely. The result? A miniature engine that doesn't just run, it breathes power. Initial tests shocked even veteran engineers. Idle vibration, near zero. RPM ceiling, higher than engines twice its size. Torque output, consistent across a wide range of speeds. In real-world trials, the tiny engine powered devices that traditionally required engines 10 times larger, all while staying cool and efficient. But Maxwell didn't stop at raw power. He integrated adaptive controls, a microprocessor that dynamically adjusts fuel delivery, ignition timing, and even microcompression ratios, depending on load. In other words, the engine learns as it runs. Testers described it like this. It doesn't just run, it thinks. It reacts before you even notice a load change. And for small-scale industrial applications, from mini generators to compact vehicles, this kind of intelligent efficiency is game-changing. Yet the story isn't just about engineering. Maxwell's tiny engine represents a shift in how we think about power. Less reliance on large, resource-heavy engines. More focus on precision, scalability, and modular design. The potential to deploy high-output engines in compact vehicles, drones, or remote infrastructure. Early prototypes were kept under wraps, tested quietly in the workshop. Only a handful of engineers and investors saw it in action. But the buzz began when a single engine was mounted on a small experimental bike. A bike that traditionally required a full-sized electric motor to reach highway speeds now accelerated effortlessly with this palm-sized powerhouse. Observers couldn't believe it. And that was just the beginning. Because the implications go beyond bikes. Miniaturization, efficiency, and adaptive intelligence open doors to entire industries. Remote power generation in areas with no grid. Compact robotics with unprecedented strength-to-size ratios. Modular transportation systems that scale without massive infrastructure. And as the prototypes evolved, Maxwell began exploring extreme endurance testing, engines running continuously for days, maintaining torque and efficiency without overheating. Which brings us to the moment the world started to take notice. The test results were leaked. Engineers from around the globe scrambled to verify the claims. Competitors questioned the physics. Investors saw a machine small enough to fit in a backpack, yet capable of powering industrial devices. And then came the most astonishing revelation. Maxwell's tiny engine doesn't just produce power, it produces profit potential. Early adopters realized that using a smaller, more efficient engine drastically reduces fuel costs, maintenance cycles, and downtime, transforming small-scale operations into highly profitable ventures. And this is where the tiny engine stops being just a technical curiosity and starts reshaping industries. Maxwell didn't just build an engine to marvel at in a workshop. He built a platform, a modular powerhouse that could be adapted to dozens of applications. In one test, The microengine powered a portable generator capable of supplying electricity to a small village for an entire day, all from a device smaller than a suitcase. In another, it was mounted on a compact drone prototype, giving it unprecedented lifting power and endurance compared to similar-sized propulsion systems. Observers noted that drones equipped with this engine could carry double the payload, fly longer, and remain nearly silent. But perhaps the most dramatic demonstration came when Maxwell installed the engine on a lightweight electric bike. This wasn't just a hobbyist build. The bike accelerated faster than conventional motors of its class, maintained torque even on steep inclines, ran for hours without overheating. Riders described the sensation as like the bike has a mind of its own, anticipating your movements, supporting you before you even push the pedals. And the more engineers tested it, the more questions arose. How can such a small engine produce so much torque with almost no energy loss? The answer lies in the combination of materials, geometry, and Maxwell's proprietary adaptive control system. Every piston is precision-engineered for maximum compression and minimum friction. The combustion chamber geometry maximizes energy transfer. Microsensors constantly monitor performance, adjusting fuel injection and ignition timing on the fly. It's not just an engine. It's a learning machine. But the real innovation isn't just in the machine itself. It's in how it can transform entire business models. Farmers in remote regions, for instance, could now power small irrigation systems without relying on diesel generators. Artisans could run mini-industrial tools in workshops far from electricity grids. Delivery companies could use lightweight cargo drones powered by the same microengine, reducing dependency on fossil fuels. Even hobbyists and inventors saw possibilities, tiny engines that could power autonomous robots, mobile labs, or emergency medical equipment. And the best part? Maxwell designed the engine to be easily replicable and modular, meaning small businesses could adopt it without multi-million-dollar setups. This tiny engine wasn't just a marvel, it was a revolution waiting to happen. Early investors quickly realized the economic potential. One engine, capable of replacing multiple larger engines, drastically cuts costs while increasing uptime. That means higher efficiency, higher profits, and a scalable technology that could spread globally, almost overnight. By the time word got out in the tech community, Maxwell had quietly created a scenario few expected, a tiny machine with the power to disrupt entire industries. And yet, for Maxwell, this was just the beginning. Because while everyone focuses on the output of the engine, he's already thinking about the ecosystem it enables, networks of machines, autonomous systems, and micro-industrial hubs powered by these compact engines. What happens when entire regions can rely on self-sufficient, powerful, small-scale engines? What happens when energy independence is no longer a luxury, but a reality for small businesses, communities, and innovators around the world? This is where Maxwell's tiny engine stops being a story about engineering and starts being a story about changing the rules of industry, mobility, and innovation. The next step was field testing, the moment where theory meets reality. Maxwell's team set up a small industrial lab in Harare, connecting the tiny engine to a series of test rigs. One engine powered a compact water pump, supplying clean water to a simulated rural village. Another ran a mini milling machine used for small-scale manufacturing. Yet another powered a drone, lifting heavy loads far beyond what any conventional micromotor could manage. Observers were stunned. Each time, the engine delivered consistent, reliable output, with minimal heat generation and almost zero maintenance required. Even under continuous operation for 48 hours, the engine showed no signs of stress. But the real breakthrough came when Maxwell connected multiple units together. By linking 3 engines in a modular system, they achieved a combined output previously only possible with much larger industrial motors. And because the engines are compact, each unit can be swapped independently, creating a scalable power network. For communities and small businesses, the implications are staggering. One tiny engine could power a remote workshop. A pair could run a small clinic. A modular array could supply electricity for an entire microgrid in off-grid regions. And for tech enthusiasts and engineers, the adaptability was unprecedented. The same engine could be used in compact vehicles, agricultural tools, emergency response drones, portable generators. And because Maxwell designed the engines to be self-diagnostic, operators could monitor performance in real time. Sensors measure torque, temperature, vibration, and output efficiency, then feed data to a central processor that optimizes the engine automatically. The tiny engine wasn't just about power. It was about intelligence, autonomy, and adaptability. During one demonstration, Maxwell mounted a single engine on a lightweight off-road vehicle. The vehicle carried a full load of equipment, climbed steep inclines, and traversed rough terrain, all powered by the palm-sized engine. Engineers in the room were whispering, "This shouldn't be possible. The physics don't add up." But the engine performed flawlessly. What makes it even more extraordinary is the cost efficiency. Conventional engines of similar output are bulky, expensive, and require constant maintenance. Maxwell's tiny engine, on the other hand, is designed for ease of production, modular repair, and longevity, making it accessible to small businesses, startups, and innovators worldwide. And here's where it gets even more interesting. Early adopters began experimenting with hybrid setups, combining tiny engines with solar panels, small battery arrays, and regenerative systems. The result? Vehicles and machines that could operate almost indefinitely in remote locations, without external fuel or charging. Suddenly, Maxwell's tiny engine wasn't just an invention. It was a platform for a new generation of self-sufficient technology. Investors began taking notice. Governments in developing countries quietly reached out. Entrepreneurs started lining up to test modular engines for micro-industrial applications. And the tech world started asking the inevitable question. If a single palm-sized engine can do this, what happens when these engines are scaled globally? The answer, Maxwell believes, will reshape industries, empower small communities, and redefine what portable power truly means. The next stage of testing brought the tiny engine into real-world scenarios, far beyond the controlled lab environment. Maxwell's team deployed several prototypes in small workshops, farms, and rural communities. The engines were attached to mini water pumps, supplying clean water to remote villages, compact generators, powering lights, medical equipment, and communication devices, electric cargo bikes, delivering goods over rough terrain without a single refuel, industrial tools, from saws to small milling machines, running continuously for hours. Observers reported the same pattern everywhere. The engine performed beyond expectations, with zero overheating, minimal noise, and near-perfect torque under every load. And the modular design revealed its genius. If one engine required maintenance, it could be swapped in seconds without halting the operation. This was not just convenience, it was game-changing for small businesses and remote operations. But what really caught attention was how multiple engines could work together. Maxwell connected 3 engines in parallel to power a small off-grid community setup, lighting, pumps, and basic industrial equipment. The system ran flawlessly for 72 hours straight, with the engines optimizing their output dynamically through a central microprocessor. Engineers were astounded. One senior observer muttered, "I've tested hundreds of engines. I've never seen such efficiency from a device this small." The implications were immediate. A single village, previously dependent on diesel generators, could now run entirely on tiny engines that were portable, scalable, and far more efficient. Next came field tests in transportation. Maxwell mounted the engine on a lightweight, modular vehicle designed for rugged terrain. The vehicle carried heavy cargo, traversed steep hills, and navigated rocky paths, all with a level of performance that rivaled much larger motors. What made it remarkable wasn't just raw power, it was the intelligent response system. Sensors in the engine monitored terrain resistance, weight load, temperature fluctuations,
torque demands,
and in real time, the engine adjusted its combustion and output, delivering smooth, consistent performance across every condition. For observers, it felt less like a machine and more like a living system, anticipating, adapting, and performing perfectly under every circumstance. But Maxwell's vision goes beyond powering tools or vehicles. He envisions a world where distributed networks of these tiny engines form the backbone of micro-industrial ecosystems. Remote farming communities with independent power for irrigation, storage, and transport. Small manufacturing hubs using portable engines to produce goods without reliance on large-scale infrastructure. Emergency response units deploying modular engines for water, power, and mobility in disaster zones. In other words, Maxwell's tiny engine isn't just a marvel of engineering, it's a blueprint for a new kind of independence. The final phase of testing took the engine to its limits: long-duration operation in extreme heat, maximum load scenarios, and continuous torque cycling. And again, the results stunned even the most experienced engineers. No overheating, no efficiency drop, no failure. At this point, the industry began to whisper, if Maxwell can scale this, he hasn't just made a tiny engine, he's made the future of portable power. And yet, while the world speculates about applications and profits, Maxwell continues quietly in his workshop, refining, testing, and expanding the potential of this palm-sized powerhouse. Because for him, the story isn't about recognition. It's about changing the rules of mobility, energy, and industrial innovation, one tiny engine at a time. Soon, Maxwell's tiny engine wasn't just a marvel in the lab. It became a symbol of practical innovation in the real world. Early adopters began experimenting with creative implementations. One rural entrepreneur mounted a single engine on a small irrigation system, allowing crops to be watered 24/7 without fuel or downtime. Another engineer attached it to a microgenerator that powered a remote medical clinic, keeping lights, refrigeration, and diagnostic equipment running for days on end. And then came transportation. Maxwell's tiny engines were installed on light electric utility vehicles, capable of carrying cargo across steep, uneven terrain. Unlike conventional motors, the tiny engine didn't overheat or lose torque. It adapted. When the vehicle hit a rocky incline or a heavy load, the engine automatically redistributed energy, ensuring smooth, continuous movement. Observers described it as, it's like the engine anticipates the terrain before you even feel it. But Maxwell wasn't satisfied with single-use applications. His vision was far broader: a networked ecosystem of engines, scalable, modular, and intelligent. Imagine a village powered entirely by these micro-engines. Lights, pumps, vehicles, drones, and industrial tools all connected to a dynamic system that optimizes energy output, efficiency, and uptime in real time. No fossil fuels. Minimal maintenance. Complete independence. During field tests, multiple engines were combined to power small manufacturing units, cargo drones delivering goods to remote areas, water purification systems in off-grid regions. And because the engines are modular, maintenance became nearly effortless. If one unit required servicing, it could be swapped in minutes, keeping operations uninterrupted. Even in harsh conditions, scorching heat, dust, rain, and uneven terrain, the engines performed flawlessly. They were resilient, intelligent, and shockingly efficient. Early investors and tech enthusiasts quickly realized the economic potential. Replacing multiple large engines with compact, adaptive units meant drastically reduced fuel costs, fewer breakdowns, and less maintenance. Scalable, flexible infrastructure for emerging markets. In one demonstration, Maxwell showed 3 engines powering a fleet of cargo bikes and small drones simultaneously. Each engine monitored and optimized its output independently, while sharing performance data across the network. The result: seamless operation, even under heavy loads. It became clear: Maxwell's tiny engine wasn't just a tool, it was the foundation of a new industrial paradigm. And while engineers, investors, and governments scrambled to understand its full potential, Maxwell quietly continued testing even more ambitious prototypes. Engines integrated with renewable sources, hybrid systems, and autonomous robotics. Because for Maxwell, innovation isn't about flash or headlines. It's about solving real problems, expanding capabilities, and rethinking what a single engine can achieve. And so, what began as a simple challenge, building a tiny engine, evolved into something far greater: a glimpse of the future of energy, mobility, and industry. Maxwell didn't just create a powerful microengine. He created a platform for independence, a machine capable of empowering communities, small businesses, and innovators worldwide. From powering remote clinics and irrigation systems to propelling cargo bikes, drones, and micro-industrial tools, the tiny engine proved that size doesn't dictate potential. Its modular, intelligent design means one engine can scale to multiple applications, adapt to real-time conditions, and operate with unmatched efficiency. And in regions where energy access is limited, it could change lives, delivering mobility, productivity, and freedom like never before. For engineers, entrepreneurs, and visionaries, Maxwell's tiny engine is a reminder. Innovation is about rethinking the possible. The palm-sized powerhouse is not just a machine, it's a blueprint for a new era of portable power. And while the world watches, Maxwell continues quietly in his workshop, refining, testing, and expanding the possibilities, one engine at a time.